Hello, my name is Mark Jessell. I'm with the School of Earth Sciences at the University of Western Australia, and I'm going to be presenting today a summary of some of the recent work that's been going on in the world of 3D geological modeling, looking at our attempts at solving some of the challenges that we've been faced with and looking towards the future of where we want to go. As you'll see, there's a large number of co-authors on this talk from across Australia, but also from Germany and Canada. And I'm going to be summarizing very briefly a lot of the different research programs that have been going on in these countries. Australia is a country that has a significant mining industry. And in this graph, which is taken, in fact, from North America, we can see that the depth of discovery of deposits, so the vertical axis is the depth of discovery of particular gold deposits in Nevada, as a function of time on the horizontal axis, is evolving significantly. In the 1940s, essentially, the deposits had to be at the surface in order to find them. But with time and with the development of new geophysical techniques and modeling techniques, we've now reached a stage where some of the deposits are being found at significant depth. And this is one of the drivers, in Australia at least, for improving our 3D understanding of the top kilometers of the Earth's crust. It's not the only one, of course, and there's a whole series of different reasons why we might build 3D geological models. And as a result of all of those different reasons, be it hydrogeological, for oil and gas, for minerals, for understanding groundwater flow, we've been making, we as a country and as a continent have been making 3D geological models over the last 1 or 2 decades. And this is a map highlighting some of the significant models that have been developed. We can also see all the black dots, which are the active mines in Australia, and every single mine in Australia will have a 3D geological model that's been built for it. The current best practice is essentially to compile all of the available data sets, so that'll be geological and geophysical, drill holes, surface mapping, whatever data is available, and to essentially manually construct the model. So there are various different pathways through the modeling process, and I'm not going to go into the detail of all of them. But essentially, it's a very manual process where an individual or a team combines all the data, and that compilation itself can take a significant time. The data is put into a 3D modeling package, and then the geologist is making a large number of decisions as to how to integrate these different data sets to produce a 3D model. Once we've got this 3D geological model, it can be used to predict a whole range of different properties. So it can be used to predict petrophysical properties so that we can calculate geophysical signals. It can be used in the mine scale to predict grade. It can be used for fluid flow studies or geothermal studies, a whole range of different possibilities. Essentially, the modern modeling process is a 2-stage process where stage 1 consists of developing a discrete model that describes the large-scale heterogeneities. So these will be fault surfaces or stratigraphic surfaces, igneous contacts, those sorts of things. And then within and between these surfaces, there will be some sort of interpolation to produce a continuous model, or a more continuous model anyway. You can see here that this one is slightly blocky, but it's essentially got continuous properties, and all sorts of different properties can be filled in within those surfaces. And this text comes from a paper in 1990, but essentially the same logic still applies, that we take our best possible data, we combine it using our cleverest geologists and the best available software, and we produce a model that allows us to make predictions of what's going on within this model. There's some weaknesses in the current best practice, and some of the weaknesses are things that were identified a few years ago in a paper that included many of the same authors in this talk. And the first one is that it ignores many types of geological data, and it really doesn't incorporate much geological knowledge in a systematic way. And I'll talk about that in a minute. The second one is that it ignores model uncertainty so that we get one model out of the model building process rather than having some understanding of where the model might be strong or weak in terms of its reliability. And the third one is that the coupling to geophysical data is quite weak as well. We have a tendency to spend a lot of time building 3D geological models and then using the petrophysical results to try and improve the model using geophysics, or we start with the geophysical data, do a straight inversion, and then use that to constrain the geological modeling processes. But there's very limited transfer of information in both cases. So let's start with the types of geological data that tend to be ignored in this process. The first type of geological data that we can think about are the geological data that are used to make 2D maps. And 2D maps are geologists' interpretation of often quite sparse data. So they are in themselves models, but they just happen to be 2D models. And on the other hand, there's all sorts of different data that a geologist will use in building a structural model and a 2D structural model, meaning a geological map. They'll use second-order structures such as cleavages, lineations, overprinting relationships, so we're getting a time relationship, the contact relationships, which will allow us to look at things like intrusive contacts, and we will use off-contact information. So perhaps 95% of the time when we find an outcrop, it doesn't actually show us the contact between rock A and rock B, but the fact that we know that that rock is there is a useful constraint on the final map that we produce. But the final map is, as I said, is just a model. But even so, we're using a rich set of data in order to make our geological maps as good quality as we can. When we get to 3D geological modeling, essentially there are very limited types of data that we can put into the 3D geological modeling packages. And for the rest of this talk, I'm really going to focus mostly on regional scale geological modeling. And the reason for that is because it's probably the least well served by the existing modeling packages. There's a whole series of packages that have been developed and commercialized over the years that are specifically aimed at looking at mine scale studies. There's a whole series of systems that are specifically aimed at looking at oil and gas systems. But there's very little software that was genuinely developed from the beginning with the idea of understanding the complexity of regional scale geology, especially in cratons and hard rock settings, where there can be many different structural events overprinting one another. And so here we have the example on the left-hand side from Lachlan Grose from his PhD that he just finished last year, and a paper that's come out this year, where we can see the types of data that we can now include in our modeling process. And we can see that we've gone beyond just the ability to look at where the contacts are and the dips of bedding, which is essentially the limitation of nearly all 3D modeling software, to being able to include things like fold axis orientations. We can include bedding cleavage intersection lineations, so similar types of information. We can have the dips of foliations that are associated with particular folding events. So we can get the richness of structural geology, which is typically used by field geologists in order to improve their geological maps. On the right-hand side, we have the work by Eric de Kemp's group from the Geological Survey of Canada. I should say that Lachlan Grose is at Monash University. So Eric de Kemp's been working on improving 3D geological modeling workflows for many years now. And the work that they've been doing recently that I'm showing here is developing algorithms that allow you to calculate contact surfaces, so this dashed line that's inferred not only from where the contacts are known, so those green dots, and where we know the dip of those contacts, those green arrows, but also by using information that is off contact. So we're doing what the field geologist does, is using the information which where we don't actually have geological contacts that allows us to interpolate a given surface. And we can imagine in the future combining these two different types of approaches to improving the use of geological data. For the example on the left, the work that's been done by Lachlan and Grose has led to the ability to propose multiple scenarios for what the 3D model might look like and what the fold patterns may look like. So just based on that relatively small amount of data on the left within those boxes, he's able to predict a whole series of different possibilities. And that's one of the keys to what we're going to be talking about in a minute, is moving away from the idea that we have enough data to predict 3D geology. The unfortunate truth is that even with all the data that we collect at the surface or in drill holes with geophysics, is not enough data to actually make a unique and accurate prediction of what the 3D subsurface looks like. And the inverse of that is that if we don't have enough data to predict what the 3D geology of the subsurface looks like, we shouldn't just make a single model. We should make as many models as those data sets will allow. And then we move on to look at how we deal with that. So that's what I'm going to talk about next. Just finally, though, before we get to those 3D uncertainty issues, we want to look at the legends that are currently used in geological models. Now, there's some legends that we can use for maps and for 3D models, like the ones on the left, where we'll have the intrusive rocks, and then we'll have some sort of sedimentary sequences with their stratigraphic relationships, and then a whole series of structural events. But the reality is that the way we need to be working in the future is to see this geological information manager, and these are ideas from Eric de Kemp again that have been published, and I'll give a list of publications at the end that refer to the different works that I'm talking about here and some other ones. So we need to move beyond a sort of fairly linear view of what the legend looks like to something that's more embedded, because each structural and deformation or metamorphic event will be imprinting over the earlier events, and these are things that geologists understand full well, but they can also be used as constraints in the future 3D modeling exercises, because we can actually understand what possible structural relationships are going to be available if we have a better description of the way the different geology is laid out. Of course, we might not have all of the information, but that just leads to some uncertainty that we can now start to think about. Looking at geological maps, one of the areas that's of particular interest to us in Western Australia at the moment is trying to extract as much information out of the map as we can. This is a fairly simple set of structures of doubly plunging folds from the north of the state. It doesn't really matter where it is. And we can see the fold axes in brown, and we can see there's a few faults that have been marked on. And as a structural geologist, we can interpret this quite easily. But once we start to look at larger areas, all of the different relationships that are contained in the map, even though we know that it's only a model of the real world, is very rich in terms of information. And so what we've been working on is trying to extract automatically all of the different spatial and temporal relationships that we can out of a map such as this. So within the purple bounded area, we can extract all sorts of different relationships, structural relationships, stratigraphic relationships, intrusive relationships, automatically, and we're doing it as a plugin for Arc GIS at the moment, but we've had various different versions of it. And so we can see these different spatial relationships that are essentially extracting the spatial and temporal topology of the map. And it turns out, and I'm not going to talk about that much here, but there's the amount of the richness of information in the geological map at the surface is something that we think we're going to be able to use as a template for constraining what's going on beneath the surface. So in the right-hand side, we have all of the stratigraphic relationships and all of the different relationships where it says all contacts. The different colors are telling us that the red relationship arrows are telling us that there's an igneous contact. The blue ones are telling us it's stratigraphic or fault-related. We can extract just the pure stratigraphy, which is on the top right-hand side. We can extract the fault relationships, so it's showing us which units are in fault contact with which other units. And we can look just at the igneous contacts. In fact, it's not obvious here, but one of these units is a sill, and therefore it's intruded and has igneous contacts with its neighbors. So those are the sorts of information that we believe are going to be useful in better constraining our 3D geology. But as I've already said, all 3D geological models are under constrained by the available data, and that's true whether you're in a sedimentary basin with beautiful 3D seismic or in a cratonic area with less beautiful gravity and magnetic data, or just with geology. So if we don't have enough data to constrain our models to a single model, we have to accept and allow and explore multiple alternate hypotheses. And that's what we've been doing here and in Monash University and Aachen University. Different groups, we've all been working together at various stages, have been developing the idea of understanding geological certainty and characterizing it. And geological certainty derives from a number of different things. It might be just as simple as measurement error. It might be the natural variability and the undersampling that is inherent in geology, or it might be through interpretation ambiguity, and we'll look at all three of those cases. Measurement error, there's a paper that came out last year comparing the scatter from measuring a fixed sandstone surface in the laboratory, 30 measurements for each instrument, so 3 different types of instrument, measuring the dip and strike of a slab of sandstone, and we can see that there's scatter between the instruments and there's scatter within the instruments, so that even if we measure in the laboratory a single slab of sandstone, we actually don't have all that precise an answer. So any observation that we have is going to be have some uncertainty. There's going to be some error. There's going to be the precision and accuracy. We can characterize it, but we can't assume that the observation is absolutely perfect. The second type of problem we have is that we have natural variability, and because we have natural variability and we don't have perfect sampling, so we often only have sampling at the surface or with sparse drill holes, our interpretation of the observation has limited value beyond the very local. So the example here is we just have a fracture in the surface of the Earth, and you've got a pen for scale, and depending on where we measure this fracture, obviously there's a whole series of different orientations that we could come up with, and depending on how much outcrop there is, we may only see one small segment of this. So there's a whole range of different possible orientations that we could imagine that this fracture has if we only have limited sampling. At the surface of the Earth, there's often, this isn't too bad a problem, because often once we get 2 or 3 different observations, we can guess what's going on in between them. But if we imagine that this wasn't a map view, but a sectional view, then depending on the luck of the draw as to where we actually sample this fracture, we might actually be significantly off in terms of predicting where we're going to be in the 3rd dimension. How off we're going to be, of course, depends on how variable the natural system is, but since we often don't have very many samples, as I said before, we often don't have very many outcrops that actually show a contact, and we certainly don't have very many outcrops that actually show a fault in plan view. What's going on at 50 meters, 100 meters a kilometer below the surface? Is the fault shallowing? Is it getting steeper? It's pretty much anybody's guess. The third type of uncertainty is what we're calling geological uncertainty, and it's related to the fact that structural geology is quite complicated in 3 dimensions. And on the left-hand side, we have a very simple system. It's a cross-section through the Earth, and we have 2 faults in different colors, and we have a bit of stratigraphy that we don't need to worry about here particularly. And we can see from the offset that fault 2 is younger than fault 1. And if we were just to say that there's some sort of geometric uncertainty, we might say, well, you know, we could just put a buffer around all these surfaces and say we know where these surfaces are plus or minus a few meters. But imagine that we actually cared about the intersection between the 2 faults, and there may be good economic reasons for that. It might be the focus of mineralization, for example. So if we assume that there's some sort of geometric uncertainty, we might fuzz up the faults and fuzz up the stratigraphy a bit. And then instead of having a point in 2 dimensions that shows where the 2 faults intersect, we might end up with circles. But going back to the previous example, imagine that we actually don't know what dips the fault have, or at least that there's a plus or minus 10-degree error in our surface measurements or in our interpretation of what they'll be doing at depth. And secondly, let's imagine that our time constraints are rather limited and we don't actually know whether fault 1 is younger or older than fault 2. In that case, we end up with a situation that looks like this, and we end up with possible intersections between the 2 faults that look like that. And so that we can see that characterizing uncertainty is going to be really important if we want to use our 3D geological models to make predictions. And if we don't want to use our 3D geological models to make predictions, it's not really clear why we're making them. So moving on, how do we deal with geological uncertainty? Well, there are many different ways that have been used in both in structural geology, in all sorts of different domains. And one way you can do it is you could just get 13 geologists to make 13 models, and that would give you some idea of the range of behavior. And this is work by Gabi Couriot from the BRGM, the French Geological Survey, and they run a mapping course where they also get the students to build 3D models. This is one cross-section through the student's 3D model resulting from his mapping from Limousin in France. And we can see that there's a little bit of stratigraphy in yellow and 2 faults in white. And we can compare that with the other 12 students. And we can see that, you know, they all came up with faults, some more faults than others. But the orientations of these faults and the resulting stratigraphy, when you include that information as well, shows a huge range of variation. So this is basically confirming what we know already, that any 2 geologists that make a map are going to come up with different answers. And when we take that to the 3rd dimension, things go from bad to worse. So what do? We need to characterize what all the uncertainties are in our system. And so they could be measurement error, they could be interpretation error, and we'll talk about that in a minute. They could even be something as simple as downhole positional error. And this is some work that was published a few years ago looking at measurement while drilling technology that's used in the oil and gas area. And so they were drilling down to 2 kilometers, a bit more than 2 kilometers at depth. And they were, based on the technology of the day, they were finding errors in the position in north-south of up to 60 meters, of east-west up to 100 meters, and in Z of up to 15 meters range. And so we can see that just even knowing where we are has got problems. In hard rock terrains, probably we're not going to be drilling that deep. But on the other hand, the difficulties of drilling in very complicated structural settings with big changes in the mechanical properties of rocks probably means that the relative errors are going to be just as big, even those shallower drill holes. The picture on the right is some work that's been submitted for publication by Evren Pakyuz-Charrier, who just submitted his PhD a few months ago, and he's working at UWA as well. And he was looking at how this uncertainty in drill hole position translates into uncertainty in the resulting 3D geological models. But I'm not going to go into more detail here. There's, of course, natural variability in many other types of data as well. And here we've got the work from Williams from 2009, looking at the range of density versus susceptibility values that you get for a series of rocks from the Yilgarn Craton in Western Australia. And we can see that many of the rock types, apart from the massive sulfides and the ultramafic rocks, essentially sit on top of each other and overlap, so that distinguishing these rocks with geophysical data is going to be quite challenging. Interpretation of geophysical data is probably one of the least well-constrained procedures in the 3D modeling process. And here we have the example of beautiful work that's been done by Claire Bond from the University of Aberdeen, where she took a synthetic 2D seismic section. So we know what the answer is, or Claire knows what the answer is. And she gave that forward modeled seismic section from the synthetic data to a number of different interpreters with different backgrounds, and asked them all to make an interpretation, and also, interestingly, to ask them to say what confidence level their interpretation has. And this person was very confident. They thought they were 200% sure of having the right answer. Of course, the other people that did the analysis also thought they had the right answer. And here's a series of different models or interpretations that were made by different people. And when she analyzed the results, she found that a whole series of different interpretations were possible. And that more than that, that the type of interpretation was related to the background experience of the people doing the interpretation. So those people who worked mostly in thrust belts were modeling this as a thrust system. Those people that most worked in extension saw it as extension, and so on and so forth. So that even with the best possible geophysical data, there is still a huge margin of error in terms of how these things are interpreted. And of course, the processing and acquisition of data gets better and better all the time. However, the interpretation is still a fairly a personal process, and that's something that we're going to have to face in terms of using these data as inputs to our 3D modeling. So what we've been doing, and this is essentially the work of Florian Wellman and Mark Lindsay over the last 6 or 7 years, is we've been running Monte Carlo simulations. And the way these Monte Carlo simulations work is that we assume that our input data is imperfect. There are different ways of tackling this problem. We could assume that the algorithms for the interpolation were imperfect, but in this case, we're assuming that it's the data itself that is imperfect. And we've seen that there is inherent uncertainty, both in terms of the measurement itself, but in how useful that measurement is in predicting subsurface behavior. So if we take our original input data and it's dipping to the south at 45 degrees, we can apply a small perturbation to that, and we can apply a second small perturbation, we can apply a third one and a fourth one, and a fifth one, or up to n here, and we can perturb all of the data simultaneously. And how much we perturb the data depends on our understanding of the inherent uncertainty in each single measurement. And by perturbing all of the input data to our models, we can produce a series of alternate hypotheses. And these different hypotheses we can then display as 3D models or cross sections. And here we've been using GeoModeler, a commercial package, where we perturb the input data And for each set of perturbed data, we generate a different model. And in the top of this window, we can see a geological cross-section, and we can see that the two faults that are extending to depth, sometimes they intersect, sometimes they don't. Various different units are in contact with each other at different times. And therefore, the range of possible 3D models, which essentially are within the estimates of the uncertainty in the input data, is quite large. So there could be uncertainty, as I've said, with respect to the orientation of data, with respect to position, the nature of the data, what the stratigraphic relationships are, what the age relationships are. And all of these things feed into uncertainty. We can add on to that the algorithmic uncertainty in the modeling systems themselves. And so we go away from developing one model to developing many models. In order to do this, we have to use a particular type of modeling engine called an implicit scheme, and there are a number of different commercial implicit schemes that are now available. All of them have the same advantage that essentially you can put in the data and then press a button to get your 3D model. Now, there's problems with that as well, and some of the problems that we've already talked about in terms of underuse of data may actually improve these systems. So what we have now is, instead of one model, we have as many models as our patience allows and as many models as our computer time is available to us. And so the challenge moves from perfecting the best possible model that we can, given our data and our understanding, to analyzing the commonalities and differences between the different suites of geological models. So how can we do this? Well, this is just one example. This is some unpublished work of Mark Lindsay from UWA, and it's a 3D model of a basin. And rather than just building his model and saying, okay, that's as good as I can do, he went through this uncertainty analysis, and he's using algorithms developed by Evren, Pakyuz-Charrier, and implemented as a plugin, essentially a plugin input into GeoModeler. And so instead of just having a 3D model, he's got a model with uncertainty. So what's just come on now is the uncertainty. Hot regions are high uncertainty, cool regions are low uncertainty. And so what we can do with this is we can see which parts of the model are the most reliable, which parts of the model are the least reliable. And what we do with that information, for example, is it can help us to understand where we need to collect more data, or alternatively, it might help us to understand which types of data have been most useful in producing our 3D model. So there's a whole range of different avenues that you can go once you understand where your model is reliable and where it's not reliable. And depending on what type of prediction you're making, it might be that your model is unreliable in an area that you actually don't care about very much, or it might be just the area that you care the most about that is the most unreliable, in which case you certainly want to be trying to understand that better. We can go beyond that, and this is work from Evren, Pakyuz-Charrier again, and you can use the model topology to classify model suites. So on the top left-hand side, we have a cross-section through a geological model, and we're going to be seeing the full model in a minute. And that cross-section, we can analyze all of the spatial relationships, just like we did in the folds that I showed you earlier on, where we were producing all the contact relationships. And rather than showing them as diagrams with arrows between them, we can replot that as a series of adjacency matrices. So these matrices on the right-hand side, we can read them as showing us what are the relationships, and it's either 1 or 0. So 1 means that two different rock types are in contact with each other, and 0 means that they're not in contact with each other for a particular model. And we can use these adjacency matrices to cluster all of the different models we've made. So imagine that we've made 1,000 different models by perturbing our input data. We can use the topological analysis to work out which models are fundamentally different from each other in terms of their topology. And what's interesting about this is, for example, the second model, the top model, is showing us the uncertainty of lithology. The middle model is doing the same, the bottom model is doing the same. So blue means very uncertain in these cases, and red means quite certain, so we're quite sure of what the rock type is. And on the right-hand side, the adjacency matrices are showing us that the second cluster actually is different from the first cluster because, and you can read this across, rock type number 5 in the columns is not in contact with rock type number 3 in the rows, whereas it was in the first cluster, and so on and so forth. So we're actually able to extract geological information back from this analysis with saying, in this suite of models, these two units aren't in contact, whereas in this suite of models they are. And we can go beyond this and we can say, how are they in contact? Is it a fault contact? Is it nonconformity? Is it intrusive? So we can build up an idea of the differences between our models and produce n-member models that we can then go and test by collecting additional data. The third thing that I'm going to talk about is the coupling to geophysical data. So, as I've said before, there's often quite a loose coupling between geophysical data and geological data in our 3D modeling and inversion. And the typical standard process for producing an improved 3D geological model will be to build an initial model based on all of the available data, to populate that model with petrophysical data, so density or susceptibility, magnetic susceptibility, for example, or maybe both, and then to run geophysical inversions on that property, on those properties. So the weakness of that is that we're throwing away all of that important geological information, the age relationships. We're throwing away information such as fold axes, cleavage orientations, and we're reducing all of our geology down into a narrow description of petrophysics, which is what the geophysical inversion schemes can use. So one of the ways that we're trying to get around that is by at least using the geological uncertainty as a way of suggesting possible models to the geophysical inversion schemes. So what we've been doing, and this is the work of Jeremie Giraud, who's just finishing his PhD in the next few months here at UWA, is we've been using the uncertainty box sets that we're getting out of our geological modeling uncertainty analysis. So uncertainty box set means that for every voxel in our model, so every cube in our model, we're able to make estimates of the likelihood that that cube will be rock type A, B, C, D, or E, and we're getting that from running hundreds to thousands of models and just doing a statistical analysis on how many times that cube had rock type A or B. And the example we're taking here is from a test case. It's originally based on the geology of the Mansfield region in Victoria, but it's been modified to make it slightly more geologically interesting, make it more of a challenge. And here we see 6 different rock types, 6 different lithologies, and we can see that there's some folds and some faults. This is in fact the same model that of the cross sections that I showed you just before. Some of the units have got the same petrophysical properties, so they're not unique in that sense. And what we need to do in terms of our integration then is we're integrating geophysics, petrophysics, and geology, and hopefully the right answer is somewhere in the middle of that Venn diagram. And the geology we're representing by not just a single starting model, so we're not giving the inversion scheme one prior model, but we're giving it the probability that any given cube, any given voxel will contain a particular lithology. So in the example here, there's 4 different lithologies, and for one given voxel, it's showing us that the most likely lithology is the blue one based on our uncertainty analysis, but that the red one is possible and the green and blue ones are possible, but that in none of our examples did the other two lithologies occur. So throughout the entire 3D volume, we know something about the uncertainty of lithology. At the same time, we also have our uncertainty about the petrophysical properties that are associated with each rock type. So in this graph here, we're showing the same sort of plot that I showed you before for susceptibility, magnetic susceptibility versus density. But we know that they aren't unique values. There isn't a one-to-one relationship between these for any given lithology. And here we have 6 different lithologies, but as I said before, 2 of them share the same properties. The cross is the most likely combination of density and susceptibility, but there's a probability density function, the PDF, for each type of lithology. And we can combine that with our uncertainty of what the lithology is to get a statistical model of what the distribution of petrophysics is likely to be on a cube by cube basis. And then we can combine that with the typical inversion frameworks that we have for working with gravity and magnetic data, which in themselves don't give unique solutions. So we have to add extra constraints. And the constraints we're adding in this case are the probabilistic modeling of the 3-dimensional geology plus the probabilistic analysis of the petrophysics. So here we have the probabilistic models for each lithology. We said there were 6 lithologies in the unit, and blue means that it's a high probability that for each type of lithology that it'll be there, spatially located as described. And white means that in the 100 or 1,000 models that we ran, we never saw, for example, in lithology 4 in the east corner, we never saw the southeast corner. We never saw rock type 4, lithology 4, occurring in that position. So these things obviously are giving us a fuzzy description of what the 3D geological model looks like. So we're combining the work of Jeremie, Giraud and Evren Pakyuz-Charrier here in order to give us an understanding of what the possible lithologies might be, and also therefore what the possible petrophysical properties are. And so now let's look at we'll look at it in 2D now, and so we're looking at a cross-section through those same models. We're just going to look at it in 2D because it's so much easier to display in PowerPoint. And at the top here, we have the true model. So we have the true density model on the left and the true magnetic model on the right, magnetic susceptibility model on the right. And the black lines are just showing us the contacts between these different units. And we can see that according to the color scale bars, that there are several units that have the same properties. Sometimes 2 units, for example, unit 1 and 2 have the same density properties but different susceptibility. Sometimes they have, such as units 4, which are occurring twice because they've been faulted, so that there's a duplication of those units. And so this is, in a sense, the truth, but it's only an approximation of the truth, because we understand now that even using our best possible data and our best possible interpretation, there's a significant amount of uncertainty in this particular starting model. So that's our starting model. And if we wanted to, we could just do classical single unconstrained inversion of the gravity on the left and of the magnetic signal on the right. And these are typical inversions that you get from unconstrained inversion systems, where it's able to pick out the first order variations in the properties, but it's doing a very poor job, and these are using the same color scales as before, just above. It's doing a very poor job of picking out the petrophysical distributions at depth. If we use the single domain inversion, so we're just using gravity on its own or using magnetics data on its own, but we add the petrophysical constraints of saying, well, we know that these are the possible rock types and these are the ranges of density and susceptibility for these rock types, these are distributions for these rock types, then we end up with something more interesting, and we can start to see that already one of the main results of this is that instead of having smoothly varying properties at for density and susceptibility, it's now produced something with quite sharp boundaries for the most part between a choice of a number of different lithologies or petrophysical properties. So that's already a significant improvement. If we do joint inversion, so what we're doing now is we're jointly inverting gravity and magnetics to produce solutions that agree with both gravity and magnetic data, but are also using the petrophysical data as a constraint. We're starting to get closer to the different structures and different units that we can see in our true model at the top. If we now include the geology uncertainty and single domain inversions, we can see that for gravity and magnetics, together with the petrophysics, we're actually doing quite a good job of matching the original inferred boundaries. And if we finally go to joint inversion with geology and petrophysics, we can see here that now it hasn't worked everywhere, and we can see, for example, that in the magnetic susceptibility, the ability to distinguish between rock types 1 and 2 is quite weak, and that's because we're at the bottom of the model and the density wasn't giving us any help because rock types 1 and 2 have the same density. So it's not a perfect solution, but it's suggesting that by integrating geological uncertainty and petrophysical uncertainty into our inversion schemes, we can make significant progress towards having geophysical inversion schemes that are actually much better at producing 3D geological solutions. If we imagine in the future combining that with taking n-member models from our geological modeling program, then we might actually end up with 3 or 4 n-member models that we can test against these sorts of inversion schemes that will allow us to understand where we need to collect new additional data to better understand the system. So everything that I've talked about up to now has essentially been proof of concepts to address known current weaknesses in the modeling system. So just to reiterate, these modeling packages ignore many types of geological data, and they don't incorporate very much geological knowledge. So there's very little understanding of the fact that we can use off-axis information to constrain our geological models. There's no real understanding of what vergence is in folds. There's no understanding of what age relationships or refolding might do to existing structures, be they cleavages or folds or faults. And there's a whole series of examples that I've cited, some of them that have been working on this type of problem. The second type of problem is trying to better characterize model uncertainty, and I've listed some of the people working on that here. And the third type of progress that's been made has been looking at the better coupling of geological and geophysical data, and there's still a significant way to go on this. In some sense, it would be nice to just throw in all of the geological data, throw in the geophysical data, throw in our codified understanding of what we think is going on in that region, and then run a large inversion system. And it may well be that that's where we're headed, but given the complexity of the problem, we're certainly not there yet. But it's certainly something that may be coming in the future. So this brings us to the sort of punchline of where we're going with all of this, is that all of these proofs of concept are nice and they're interesting, and they certainly suggest avenues for future research, but a lot of them require fundamental recoding of the existing modeling systems. The modeling systems, most of them are at least 10 years old, some of them are 20 years old or even older, and they weren't really set up to do this sort of modeling, the types of things that we've been discussing today. And so, thanks to the support of the One Geology Consortium, and the One Geology Consortium is an international consortium of national geological surveys that many people will know because they put out a web portal that allows people to download 1 to the million geological maps of the world, not from all countries, but from all the partner countries, which is a significant number of them. And they understood as geological surveys that, of course, geological maps are never going to lose their importance, but there's an increasing emphasis on the need for 3D geological models. And since they, as geological surveys, are very concerned with regional geological data and 3D regional models, they came to the conclusion, as we had done, that the current systems weren't really appropriate. One other aspect that they deemed very important is that the current systems are commercial, and they wanted an open source solution so that in their roles of providing geological data and geological knowledge and information to their countries, that having an open source solution where anybody could take up the three-dimensional geological models and modify them or include their own data was an important aspect of the system. Going beyond that initial One Geology Consortium, we've now received additional funding. We've just recently found out that we've received an Australian Research Council funding to support this. The Geological Survey of Canada is also funding positions, as is Geosciences Australia. And at more or less the same time, one aspect of the MINEX CRC, which is an Australian cooperative research centre, is going to be looking at developing automated 3D geological modelling systems. And it's part of this same consortium, and this consortium is known as the Loop Consortium, and it's going to be developing over the next 10 years a new open source 3D geological modelling platform. And it's going to, of course, incorporate the ideas, if not the detailed code, from all of the different types of analysis that we've been talking about so far. And this project is being led by Laurent from Monash University, an old friend and colleague who's been working with us on these programs for a long time now. And it involves a series of organizations, geological surveys and universities from around the world. And we're, of course, because it's an open source program, we're very open to collaborating with researchers in terms of student projects or parallel funding opportunities, and we've got our contacts there at the bottom. So the future of 3D modeling, at least for the people involved in this project, is going to be taking everything back to a base level and saying, we're going to start from scratch, but we're going to be looking at where the world is going to be in 10 years' time. So we know it's going to take us 10 years, so we need to be thinking about what computing systems are going to look like in 10 years. Are they going to be increasingly parallel? Is there going to be any sort of quantum computing available, which would match very well with the uncertainty work that we're doing, the Monte Carlo simulations? Is 3D modeling going to essentially be a black box where we have a database of information, we input our conceptual ideas as to what we think is happening, and then it produces a suite of final models? How much data analytics are we going to involve in the data prior to producing these models? All of these things are going to be discussed as we start this project in the next few months. So that's really the summary of the of the new project that's more than proposed now. It's actually up and running. And we're certainly interested in hearing from partners around the world that may want to work with us on this project. So just to finish off now, I'm going to just to provide a list of some of the papers that I've been talking about. You can see there's a whole range of different authors. Many of them are sharing authorship between groups, and that's really been the strength of the consortium that was set up, is that it's a group of people that have been working together for quite some time now. So I think I'll leave it there. Thanks for listening. And of course, if you have any questions, you've got our emails and you can contact us for comments and discussion. Thank you very much.